Okay, we are very pleased to have Wesley Maciejewski today. He is from Red Deer Polytechnic, and he will speak about advancing undergraduate mathematics education. In which direction, at what speed?
That's right. Thank you, and thanks for the invitation. I guess I'll just, so I have slides, so I'll just share my screen. Okay, and you let me know if that's becomes problematic at all. Okay. Should be able to see that.
Yes, looks good.
We're good?
Yes.
Great. Okay, let's begin. So, I remember Zoom used to have this problem where the windows that I can see you in might obscure some of my slides. So let me know if anything gets covered up at all. Okay, and just interject. Okay, so yeah, I'm Wesley Maciejewski. I've had a bit of a journey in my career. At the start of the pandemic, I was a professor, an associate professor in San Jose State University in California. But you know, the pandemic turned everything upside down, and I ended up back in Canada, in my home country, in my home province of Alberta, at Red Deer Polytechnic, and that's an image kind of in the middle of Red Deer Polytechnic. Okay, and it's a very small, rural Canadian college that offers university degrees and some math courses. Okay, but when I arrived, well, let's back up just a minute. At San Jose State, there was a lot of curriculum reform, partly because of the California state outlawed developmental mathematics. And so our department had to deal with a lot of curriculum reform and really question what we were doing and things like this. And so that's what I was engaged with for the last 5 years. And when I came to Red Deer Polytechnic, I encountered a fairly traditional offering of courses in that you might see at any institution in the first 2 years. And so that really foregrounded a lot of the things that I had been thinking about in terms of undergraduate education in the last few years. And it makes me question, you know, where I am, what I'm doing, and where it's going. And so that's what this talk will be about. Now, I'm sure all of you have encountered criticisms leveled at undergraduate math education, the courses, and the educators. I'm sure you've seen these. These have been around for ages. You hear the complaint constantly, oh, I have a second-year student and he doesn't know what an exponential function is, or she doesn't know how to differentiate a polynomial or something. Or you might hear, oh, your curriculum isn't relevant to my students as biologists, or, oh, you're lecturing too much, or you're covering too much material and you're not going too in depth into modeling or something like this. These are kind of standard complaints that if you stand around the water cooler long enough, you'll hear all of them within a day, I'm sure. But I think we shouldn't take them lightly. I think we should really put our own practices under the magnifying glass and see what we're doing and how we might do better, not to appease the naysayers, but to just really improve what we're doing and really come up and shine through and make sure mathematics retains its relevance and is engaging, and what we're doing is in fact effective. Okay, so what I'll talk about is broadly divided into 3 themes: the delivery of our courses, the assessment within our courses, and then the curriculum within those courses, okay? And like I said, I just want to take a snapshot of kind of contemporary practice and kind of trouble and question where we might be headed or where we might want to head. Okay, so I'll focus on delivery first. And I'll also keep an eye on the time. My goal is to reach the 40-minute mark, but if I talk too fast, it'll be much sooner. Okay, so here's a picture of my math class that I took just an hour ago. You can see some of the students are on their phones. There's some talking in the back, not really paying attention. There's some poor guy here is sleeping. So they're generally having a good time in calculus. I would say, of course, this wasn't my class. I'm not sure the age of this painting, but it kind of reveals that what we're doing by and large hasn't really changed in the last long time. That's not to say that people aren't doing things differently now, that we don't have more progressive forms of education. But if you were to take a poll of, let's say, all college math instruction in North America or even the United States, if you were to just to walk into a random class at a random university or college somewhere across the country, you would more or less see this image. Okay, math is primarily taught through lectures. It's assessed primarily through summative assessments, high weight, final exams, closed book, etc. And math is primarily calculus. That's our primary enterprise in post-secondary. And there's a very strange peculiarity in the USA that most colleges and universities offer a ton of algebra courses, which ought to have been a prerequisite, but isn't, is still maintained as a college level course, whether it's college bearing or not. Now, I think this is for me, problematic in the sense that right now, in terms of the whole of human history, I think that math is at its golden age. The things that we're accomplishing as humankind, they're all based on mathematics, okay? Machine learning, artificial intelligence, space travel, advanced economies, these are all based on mathematics. Yet we're teaching things that are, in my opinion, entirely disjoint from all this really interesting action that's taking place within the field in terms of applications, but also in terms of development of mathematics. And I think that's very problematic. Okay. So lectures being the predominant form, it doesn't mean that that's the only way we could do this. There are far more diverse and other ways of delivering content than just lectures. We could, for example, do problem-based learning or project-based learning, a very widely accepted and kind of traditional within the mathematics community is the Moore method, having students push forward the action themselves. And then there's this kind of catch-all phrase, interactive engagement, where we're having high levels of activity in the classroom that the students are engaging with. So rather than a kind of a transmission of the lecturer to the students are actively working on problems, they're actively interacting with the instructor, and they're driving the action in the class time forward. So it's very student-centered and student-driven, okay? And I just highlight here a very well cited, very famous paper when this came out. I'm sure that you're aware of it, this Freeman PNAS paper, where it looks at active learning across STEM disciplines. And they show quite a significant difference in student learning and student gains across all subjects when they experience interactive engagement in some form. Now, like I said, this is a catch-all form. It doesn't mean any one specific thing, but refers to a whole suite of possibilities. And one such thing is this classroom flipping. Okay, and so this is something that I was heavily involved with when I was in my postdoc at the University of British Columbia years ago, but around the time that this Freeman paper came out. Okay. So what is this exactly? Well, it's, effectively, it's your students come prepared to class, and then in class, they interact about the subject matter, okay? So what happens is before they come to class, they read or they watch videos or what have you, they encounter the material in some form before they come to class. So the content that was typically delivered within the class time is now delivered out of class time. And it can take many different forms, like the form of this clip art here that I found on the internet. the student is doing calculation and thinking about parallelepipeds and things like this. So this is what they would do before they come to class. Then importantly, they're quizzed on this material before they come to class. This could be just a few questions. It could take place as a daily assignment, multiple choice, free response, depending on the size of your class and the amount of resources you have available. But the key thing is not only do they just passively read or passively watch videos, they actively are answering questions on the material they encounter, okay? And so this is designed to ensure that they have some sort of base that they can work from when they come to class. Now, in class, this is devoted to solving problems, answering questions, interacting with the instructor, interacting with other students. And what is de-emphasized is the delivery of new material. So the lecturer or the professor doesn't walk through problems themselves. They don't introduce new definitions. They don't introduce new theorems in class. That was already done outside of class. That class time is devoted to exploring problems related to the material, applying the theorems in class, et cetera, et cetera. So a lot of action takes place here. I have a picture here of course, a clicker. These were all the rage for a while. I think you can mostly get cell phone apps now, which are a little more convenient. But for example, at UBC, that we had a high level of classroom flipping in the first few years. What we would do is all of our class time was devoted to multiple choice questions that were really carefully constructed so that among the 4 responses, the students would normally achieve a uniform distribution. So it gave them a lot to discuss. And then after we do an initial voting round on the question, I would prompt the students, I would say, okay, now turn to your neighbor and don't discuss. Discuss is a vague instruction. I would say, convince your neighbor that your solution is correct. And so they would start arguing for the solution they put up. And if they're arguing for an incorrect solution, that is relatively quickly exposed to them. And then they can revise their responses for a second round of voting. And you normally see convergence to a right answer after that discussion, okay? And to make sure that the students maintain the gains that they experienced during the class, there's a post-class assessment, okay? So that's kind of a general overview of that. I'm not going to go into specifics here because I'm going to talk more about other things that's going on in post-secondary, but just some kind of doubt cast on on being able to actually implement classroom flipping. I often hear, my class is way too big, no way I can have interactive engagement. My response to that is that no, it's not too big. In fact, the bigger the class, the better, because classroom flipping really does handle large classes very effectively, okay? It's worth trying out. What about rigor? There's always the concern of you're watering down the mathematics curriculum. My response is, what about it? I think you can maintain that if you ask the right questions and structure things correctly. And really the big genuine concern about something like classroom flipping is I don't have time to do it. And that I am very sensitive to, because when you set out on flipping a classroom, it takes a lot of time. That initial time investment is huge. But fortunately, the time required after that diminishes dramatically. Second iteration of a flipped classroom course, there's essentially very little effort put into that the second time around. It's just getting it set up the first time. So this works perfectly if you have multi-section courses that are coordinated. You can have a team develop the course, and then it's used by everybody collectively throughout the year. And then you'll find that if everyone's lifting at the same time, it's actually quite a light load, okay? But that is a very real constraint, having resources in a chronically underfunded system. So it really is a matter of, well, where does the department chair want to put invest their money? I think classroom flipping is, in fact, a great investment because the returns are really good. I just came across this survey on the left. the flipped classroom, a meta-analysis of effects on student performance across disciplines and education levels. And sure enough, it kind of corroborates what I found in my article from 2015, that there's pretty good positive effects on student learning gains from the classroom flipping model. Okay, and that's across STEM disciplines. If you see any references in here, excuse me, that you are interested in, I can always send you them afterwards. You just send me an email. But let me talk quickly about math specifically. So I had performed this study at the University of British Columbia about 2014, 2015, where we were looking at the effectiveness of classroom flipping. And so we had essentially a control group trial as best we could with control. And we had, I think, 4 sections were flipped and 3 were not. They were very traditional lectures. And so we looked at the student outcomes from those 2 treatment conditions, okay? And we used final exam scores, which are imperfect, but we looked at those. And we also looked at the calculus concept inventory, which is something that's no longer maintained, but it was kind of there to mirror what was happening in physics in terms of the force concept inventory. So we looked at gains, and now the top is the kind of the aggregate across all sections. We just looked at the 2 flipped and not flipped and looked at the difference. And you can see the final exam, there's an 8% difference in favor of the flipped classroom. And this is statistically significant and has a pretty decent effect size. Okay. There is a difference in terms of the calculus concept inventory for the flipped versus the traditional. There's a small difference there, which is statistically significant. But if you look at the gain in terms of how much students gained based on where they started, there isn't a significant difference here. Okay. So that's kind of somewhat interesting to see a performance difference like that. But in my books, nothing to write home about. To me, where the action really was in that course is down at this table 2. So what I've done is I've sectioned up the students into quartiles. Every student had to enter this basic skill, and every student had to write this basic skills test upon entering university. And this is on background knowledge. Kind of in America, you might see it as like what we used to use as like developmental math placement. So they would write this basic skills test that would tell them where they're going. But at UBC, they didn't stream students. They just wanted to collect that data to see where they needed to invest support and things like that. And the students, upon entering the calculus course, wrote this calculus concept inventory. So I have, like I said, have the students broken up into fourths. So they're into 4 groups. Those with low basic skills test scores and low calculus concept inventory scores, those with low BST, high CCI, high BST, low CCI, and high BST, high CCI. And to me, this is where the flipped classroom model really shines through and takes care of actually a lot of some of the concerns that people voice, that it might hold back the top performing students, for example. Let's look at this. So these lower end students, low BST, low CCI, there they see final exam difference of about 7%, and that's statistically significant. They also see a really large gain in the calculus concept inventory. Here they're seeing a massive, statistically significant gain in calculus knowledge relative to traditional lectures, okay? The other students that seem to benefit are those that have high basic skills but low calculus skills upon entry into the course. There we see another large gain in final exam scores over traditional lectures, and also a statistically significant gain in CCI scores, okay? This other high BST, high CCI, so these are students that are, probably good from high school that have taken calculus and did well in it. Nothing is statistically significant. So there's no difference between the flipped classroom and the traditional lectures. The students were going to be good no matter what we do, is the answer there. Here we have low basic skills, but fairly good calculus knowledge coming in. And again, we don't see any statistically significant differences. So we see really the true beneficiaries of the flipped classroom model are our weakest students, And so this is, to me, something to write home about. This is really why we might want to go and flip our classrooms. We benefit those that need it the most. Okay, let's move on to assessment. So I think rather unfortunately, we still assess our students in very traditional ways, writing timed exams, for example. This is problematic to me because if you interview any mathematician, they'll tell you, oh, calculus or math is beautiful. Math is deeply conceptual. It's a very creative field. Well, guess what? If you're not assessing on that, if your exams aren't beautiful or creative, then you're a hypocrite. Our students come to know math in terms of how we assess it. We can take it as axiomatic. If no matter what we say of how beautiful it is, if I give an exam that is all differentiating a list of functions, there's no beauty in that. And the students will come to know math in terms of how we assess it, okay? And now this is what's particularly damning, I think, is if we analyze the types of questions we give our students. Now, I had done this a few years ago, and other researchers like Tallman, who I think is in Oklahoma right now, had done this, where they looked at the types of questions we give our students. And what I did here is applied, for example, Bloom's taxonomy to see what sort of cognitive demand level each of the questions are on. And what we found when we looked at historically, it was like 5 years of final exams that were handed out at UBC. So a ton of questions that we went through. Roughly 80% of questions given to first-year students only involved applying something. So like finding a derivative, calculating this and that. The good news is there's very little memorization involved, but there's also very little understanding involved, and less of the higher order skills that are picked up in Bloom's taxonomy. In particular, there's nothing that requires first-year students to create anything new in mathematics. Very little involves evaluating, okay? But perhaps what is also troubling is that even at the third and fourth year, our emphasis is still on applying things. So still calculating things, very little on evaluating things, very little on assessing things, still geared towards very traditional type, solve this problem type questions, calculate something, okay? I would argue that that's not really what we want our students to do, especially our math graduates. This is 2022. Wolfram Alpha is out there. It's far, far better at differentiating than I am, than any of my students are. And so I really would be doing them a disservice if I was having my calculus students turn into derivative finding machines. No, we have computers to do that. What we ought to be focusing on are higher order skills, having some sort of evaluation of biological models, for example, or creating models, modeling the stock market or something, or perhaps modeling artificial intelligence or something. These are the skills that computers can't do, that our students should be doing. So we ought to identify those and create not only educational experiences that work towards them, but assessments that assess on the skills that we really value. Because really, like I said, we need to put our money where our mouths are. Our students will know the field by the assessments. Okay, so one very popular way of doing this is through this constructive alignment of John Biggs, where we explicitly state what we want our students to do. We want them to develop their own biological models. And so we create activities that help the students develop that, but then we assess aligned with our learning outcome. So then the assessment isn't on, find the equilibrium in this model that I give you. The assessment would be create a biological model, okay? Then we would have constructive alignment. The intentions that we had at the outset are then assessed, and our students see that, yes, indeed, what we were talking about is what's important. Okay. One possibility for this type of activity, for me, what I think is very important, because it's somewhat inescapable working within our current confines of the curricula that we have. One thing that we could do within those confines of like offering calculus courses, which are extremely procedure heavy, and I would argue not particularly conceptual. One thing we could do in those courses, for example, is try to promote procedural flexibility, where students don't just rotely take derivatives, rotely perform procedures, but that they're required to do things in different ways. Okay, so they might be asked to differentiate a function like this function I've got up here. They might be required to differentiate it in 3 different ways. Show me how it could be done with the quotient rule. Show me how it could be done with the product rule. Show me how you might do polynomial division first and then use a power rule or something like this. Okay. Now, what the strength of this is that we create students that have a certain perspective of mathematics. If you go and interview any of your students right now, they'll tend to give you very rigid responses of what mathematics is. Mathematics has a math question has only one right answer, one right solution. And they tend to not see that an answer could be got with multiple different solution paths, okay? So if we value that, if we value our students having flexibility of mind and having this perspective that you could have multiple different solutions to arrive at an answer, then we could emphasize that through something like this procedural flexibility, which I'll show you an activity of briefly. Okay. Oh, and one thing I should identify here is that a recent study of mine has shown that those students that are flexible problem solvers tend to be more confident as well. So if we want to address the math confidence epidemic, one way to do it is really promote this type of flexibility of problem solving, flexibility and mindset. That seems to be strongly correlated with confidence. Okay, in terms of causal relationship, I'm not sure yet, but there is a strong correlation between confidence and flexibility. We also find from other researchers out of Harvard and Vanderbilt that having flexible procedural knowledge actually promotes further and deeper conceptual knowledge. So this seems to be like something that ought to be low-hanging fruit that we could gear our courses towards in the first 2 years to promote deeper learning for our students. And I'll give you an example here on the right. This is a worksheet from my current calculus course that I just ran from to be at this presentation. So I say, find the derivative of the following. It's this rational function there. And I have them do it in 3 different ways up to them. So they might want to do quotient rule. They might want to do polynomial division. They might want to write it as a product and do a chain rule or something like this. And then once they solve it in 3 different ways, I get them to comment on which one they prefer. And the idea here is they need to reflect on, oh, this is better because of this reason. Oh, this was more appropriate because of this reason. And, you know, you're going to have a variance in which solution method students prefer. It tends to not always be one way all the time. And the key thing here is through this activity, you're promoting that kind of reflective flexibility of mind, okay? And sure enough, one of the studies I highlight here is that just by using this in your assignments, students end up being more flexible solvers later on. So it seems like it's something that a very slight variation on what we're doing already that can promote deeper student learning, okay? And something we can assess on. Okay. I'll talk about, I think we're good for time. I'll talk one more thing that I've developed over the last couple of years, which I'm still using. I want you to think, when you're about to embark on a new mathematical research project, or, you know, maybe you encounter something, you forget how to, you know, solve a particular partial differential equation, or, you know, something like that. Or perhaps you're about to go teach something and you forget what Cayley's theorem is. So what do you do in that situation? Well, that's right. You look it up. And I don't know if any of you have kids that had watched this version of Elmo. There used to be Elmo's World a few years ago, which was fun. And they had a kind of a very routinized way of doing it. They would last for about 20 minutes. And then there was like an Elmo's World 2.0, where they would be only like 6-minute segments. They're all research informed. And we found that people only have about a 6-minute attention span for these types of videos. But in these videos, you know, a typewriter would ask Elmo, oh, do you know what this thing is? And he'd be like, no, I don't. So let's go look it up. And he would whip out his cell phone. Elmo would take out his cell phone and he would Google the question and he would come up with something and he would learn about it. I think this is the greatest kid show ever created, because this is what humans do. This is what mathematicians, this is what people with PhDs do. They admit, I don't know what that is. I'm going to look it up and I'm going to learn about it, or I'm going to go and use the information I looked up and solve the task at hand. There is no reason why our students should not be able to do this during exams, period. It's 2022. They have the sum total of human knowledge in their back pockets. They should have access to that. And so that's what I've done. This is a paper that appeared, I think last year was the publishing date, or a couple of years ago, forget now, where I do exactly this. In a differential equations course, I allow my students to not only use their notes and calculators, but also Google things, look things up in the exam, so that they have all the resources possible, except for other people. They can't ask other people, but they have all these other resources available to them, okay? And it seems to have been successful. I still do it to this day, that I let students use whatever. And my argument is, this is really what the real world looks like. And so there's no reason why what we're doing in university should be somehow special, should not be the practice that they're going to experience in their careers or their academic lives later on, okay? Now, part of my motivation for doing this is to move assessments away from this very routinized, very rote, find the derivative type thing that Wolfram Alpha can do. If you know that your students can access Wolfram Alpha, are you going to give them a list of derivatives? Well, you're not. My argument is you're actually going to give them more meaningful, higher order questions on the exams. And this is why I did this. I really wanted to kind of force myself to move away from those very procedural, very uninteresting problems that are better solved through an online calculator, and ask questions that only humans can solve. Ask those of my students, okay? And so I do that to this day. And here are some examples. Here's one for a class of future teachers. I've got two numbers raised to two different kind of sequences of powers. And I ask, which one is larger? Okay. And I want them to do it without calculating the numbers themselves. I say, which one of these two is larger? And so what I'm looking for here is an argument. I want them to say, look at, you know, I could do this, I could do this, I could bring it down to realizing that I'm only comparing 2 to the 3 and 3 squared. Okay, so I'm really just comparing these, and the other powers don't really matter. Okay, but the point is, I want an argument. I don't want a calculation. Okay, and I grade them on their argument. Here's another one. Explain why this power goes into the brackets like that. Okay, explain that. And they only deal with natural numbers, so I restrict it to natural numbers. But explain why that is. Okay. Sure, yeah, they can go and look it up and look it up for an explanation on the internet, but they have to reword it. They have to make it their own. Okay, and that is the process. That is actually what we want from these future teachers. Okay. Okay, now I'll talk very briefly about curriculum. I took some screenshots here. So this is your catalog on the right: Introduction to Algebra, Elementary Algebra, College Algebra, Calculus, and so on. On the left, here's San Jose State College Algebra, Trigonometry, Calculus. And here's where I'm at right now. So preparatory math, algebra, calculus. We're all doing the same thing, is the point. It doesn't matter which institution you walk into, we're all offering the same kind of courses. Okay. Is that is that something we should be doing? And if it is what we're offering the kind of the most appropriate thing at the time? I don't think so. I have quite a few problems with our current standard offerings. And what I think we've fallen into is this kind of trap of tradition, that we offer things because of course students need calculus in their first year. That's what they study. But we haven't really put that under the microscope. We haven't really evaluated, is this something that we need to be doing? Okay. And I like this quote from this recent article of Brasoud, who says, "For too long, the emphasis in mathematics classes has been on what is easy to test, rather than the kind of knowledge that students actually need for subsequent work." I think this is truth. This is why we offer far too many algebra courses. We say this is what we need students to do, not because that's what students need to do. Guarantee you they do not need to know the quadratic formula, but we give it to them and we assess them on it because it's easy for us. Okay, and so this is something that we really have to confront, which is an uncomfortable truth. Okay, so the one thing that I questioned when I was at San Jose State, when the state handed down this decree that developmental math was no longer legal, that we couldn't offer it as a college course, I started questioning, well, if we can't do this traditional course, we shouldn't see what kind of curriculum is out there that we should look for to give these students. Rather, we should think about the skills that we want our students to have. And then the curriculum built around those skills is kind of window dressing. It's kind of this thing that has a limited life. As long as we have the core skills down, we can package them in a calculus task. We can package them in a graph theory task or something like that, as long as we're getting down to those core skills, dispositions, or knowledge. Okay. So here's an example of what we offered at San Jose State in place of college algebra. We did modeling of the pandemic at the time. This is me online in California. We had to go online, teach on Zoom. And so what I did is took a current event, the COVID-19 pandemic. This was in 2020. And we modeled it. We looked at statistics. We looked how it was spreading. We used disease spread on networks. We looked at these types of things. And it was accessible to these students rather than just give them the same old college algebra. Look we're doing algebra here. This SIR model is just algebra and we're doing it, but it's relevant and it's contemporary, okay? Or here we work out kind of a Sierpinski triangle where we're taking out triangles all the time and ask what kind of patterns emerge when we, in terms of how much area is remaining or how many triangles are being cut out. Again, algebra, we're not teaching algebra in the traditional sense. We're having students develop the algebraic skills that we think are necessary via activities that are meaningful or engaging or what have you. Okay, and now really the big elephant in the room for me, having just come out of a calculus course, is that I really think there's something staring us in the face as mathematicians and math educators. We teach too much calculus. And I strongly believe we need to give that up. We should be not doing that anymore. I understand, I know what the role calculus has played in the history of humankind, how it was really a very profound event. I always tell my students, there's no wonder that the Industrial Revolution happened after calculus, because calculus allowed us to develop machines predictably and allowed us to develop economies, large economies and things like this. So there's no question in my mind that the advent of calculus was a turning point in human history. However, this word has come to mean something else entirely. It doesn't mean that profound thing anymore. It means having our students differentiate or integrate a list of problems, doing all sorts of arcane trigonometric integrals and all this stuff that is better suited for computers and not for our students. And again, I quote Brasoud here. in calculus then, in the past, as too often in calculus now, the focus has been on learning how to differentiate and integrate and solve a standard repertoire of problems. It is, and it really is, because it's easy for us to assess. So then what should we do if it's not calculus? It's really, it is very difficult to imagine if our culture is so steeped in that. It's difficult to imagine anything else. And we can always excuse away the importance of calculus. Oh, they're going to need it to find, radii of gyration in their physics class in third year. We can always find some sort of excuse to keep it going. But what I would argue is that we really ought to think about what are the foundational fundamental skills and dispositions we want for our students from the experiences we give them. I think calculus doesn't offer any of those skills we want them to develop. It really offers them how to do things rotely and learn procedures. Maybe learn some algebraic skills, but those are passé. Those are not relevant skills anymore in 2022 and moving forward. So we ought to really devote our time to conceptualizing what skills we want our students to develop. Not only that, how we want them to feel about math. Do we want them to see it as a beautiful subject, a creative subject? Then we ought to be doing beautiful and creative things with them. What type of knowledge do we want? What do we want them to know about math? Maybe we want them to know about what infinity is, or how many numbers there are, or how to approximate the discrete with the continuous, things like that. So once we identify those, then we are in a position to think of the curriculum. It might turn out that we still include some of the calculus in the curriculum moving forward. But that's, to me, the question unanswered. What is it that we want our students to get out of our experiences? Okay. So I'm just going to wrap that up, and I think we have still plenty of time for a bit of a discussion. Here's the takeaway. Okay, so the how of post-secondary mathematics education in terms of the delivery and the assessment, I think that's quite well developed. I think there's a lot out there that we can go on in terms of how we should deliver our courses, how we should assess our courses, what type of experiences we could give our students. But I think the thing that we've really skipped over while we're looking for the how is the why. Really, what is it that we're doing? Is this really something we want our students to get out of an education that we offer? So, and I should actually make explicit, I don't have an answer to that either, of the why. I don't have an answer of the skills that our students should take away from the courses that we offer, but I'm working on it. And I implore you with this final conclusion here to do the same. So every derivative you find, every definite integral you have your students calculate, ask yourself, why? Okay, there we are.